random source used, but I think that was
that was older. This wasn't the same issue. Because I did check that to make sure that that wasn't the issue. But yeah, I did some tests on some other processes and didn't see the same exact behavior. So I'm not really sure what causes it, and I haven't spent much time looking at it. It's just a kind of an interesting thing that I noticed. So ASLR can be defeated because it's only as strong as the application profile. And for example, I found that the profile used for events thumbnailer, that allows you to write files to the .config/autostart directory, that's another one of those things that shouldn't exist in Linux. It was an idea that was copied from Windows. And that is basically the same thing as the startup folder in Windows, where you can drag an icon to it. Every time that you log into your machine, it will run this script. So if you can write an exploit for events thumbnailer, that you can bypass AppArmor by writing a file, writing a script to the AutoStart directory that will run every time the user logs in. So in that case, you could plug in your USB key, let the exploit run, and then just turn off their computer and wait for it to log back in. And I did file a bug report for that, so they did fix it. And so the latest, I think it's Natty, yeah. So it's fixed in Natty. It's not fixed in Maverick. But there are also some things that AppArmor can't protect against, and these are IPC type of issues. The one that I was looking at was with X11 library calls. So in that case, if you're not allowed to kill a process yourself because the AppArmor profile won't let you launch the kill command, it won't let you read from the proc directory, it won't let you use the ptrace system call. So there's a lot of things that you can't do to prevent you from killing a process. But what you can do is use the X11 API calls to enumerate all the windows on the desktop, find one to kill, and then kill it. So I was able to use that to kill the screensaver. And so you can also use X11 library calls to snip keystrokes or even inject keystrokes. There's a lot of, you might be able to rewrite files. So there's a lot of bad things that you can do with just the X11 library. And something else that I would really like to spend more time looking on is other sort of IPC mechanisms like UDEV or dbus. There's a lot of services that are provided that give you a dbus interface for communicating with that service. So if we can find something that's not authenticated, then you can use that to bypass AppArmor by. The way that it works is, so in the X11 example, it's the X server that does the work of killing the process and not your own process. So the X server isn't protected by AppArmor. That's how it works. So what sort of things can you do once you have a successful Autorun exploit? One thing you can do is just copy files from the user's home directory. So if they have full disk encryption, if they're using TrueCrypt or something, and they have a disk mounted, or if they have installed their browser cookies or documents. So that's one method. That's one thing you can do with your exploit payload. The thing that I like to do is kill the screensaver process. If you can run a command, kill all known screensaver, does it. And that will give you full access to the user's desktop. And it's not as easy to do that on Windows. In Windows, the screensaver isn't just another process. They have some pretty interesting security layers that prevent you from getting past the screensaver. But in Linux, it's basically just a process that has the root window and it doesn't let you get past it. And if you kill that process, the screensaver goes away without having to type in a password to unlock it. Something else you could do is install a backdoor. You could add a script to the dash profile file or the profile file. You could add a desktop file to the config.autostart, config/autostart, which I mentioned before. And if you have access to another local exploit, you could use that to install the rootkit. So there's all sorts of different things you can do with your Autorun payload once you have an exploit working. So a couple different ways to kill screensaver. Like I said, it's just a process that runs in a window at the top of the X11 window tree. You can kill the process, but you can also use the X11 library. You can call xopen_display, xquerytree, xfetchname to search for known screensavers, then call xkillClient and that will terminate the screensaver process. Thus, you can use that to get around AppArmor's protection from launching other processes. So another idea is installing a backdoor. So even if you don't have root access, like I said, there's a config autostart. It's like the Windows startup file. The shortcut files in Linux, like the LNK files in Windows, are desktop files. .desktop file is just a text file. It's a pre-desktop.org specifications tell you how to do it, but it's pretty easy. It's pretty easy to do. Or you can just use the .profile or .bash profile, or look for other files that might be left unprotected by ASLR. Or you could have your exploit download some other remote access version or copy one from the USB drive. So there's all sorts of ways you can install that on a system with a successful exploit. So now I can talk about some of the vulnerabilities that I found while doing this research. So these were there were 4 of them, and they were in edicts. Ubuntu published an advisory for them, and so the vulnerabilities were in the handling of DVI documents. DVI files are generated from latex documents, and nobody uses that format, really. Like, I tried to search the web for examples of DVI documents, and I found a couple of them, but nobody really uses that format. People either use PostScript or PDF. So I don't know why they automatically parse those. So DVI files can also reference external fonts that get loaded when the DVI file is processed. And the fonts can actually be specified in that file with an absolute tab. So there's a lot of things here that shouldn't be happening. And I actually found out that it was easier to exploit these bugs from USB than any remote vector because of this fact. So the one bug that I found, the easiest one to exploit, was an issue in the PK file font parsing. And this code was part of a library called mdvlib. It was written in 2000. It was written 11 or 12 years ago, and the code's all pretty bad. I gave up after finding 4 vulnerabilities because I just didn't feel like reporting anymore, and some other people did find some more in the same area of code and reported them. This specific example is, this one was pretty easy to spot. I didn't use a buzzer or anything. I just opened up the source code and started looking at it by hand. So there's an integer, int.cc, it's an unsigned integer, and that is read from the file. FU-get4 will read a 4-byte integer from a file. And FU-get4 actually returns an unsigned integer, but because CC is signed, then it's possible to have a negative value in that file. So keep in mind that CC can be negative. And there's also some other values, W, H, X, and Y, that also get read from the file. And this is a problem because it's using CC as an index into an array. And so you're basically able to do kind of an arbitrary write. There are some checks for CC to make sure that it's not too big, or to make sure that it's not too big, fall outside of the higher bounds of the array. But there was no check to make sure that it was negative. So you could have if your file has a negative value, it's possible to write some arbitrary values. Remember the W, H, X, and Y were in the file. You can write arbitrary values to some structure in memory. Something else interesting about this is that it is because it's an arbitrary write. It's you don't have to worry about. There's an issue with you don't have to try to guess random addresses with ASLR. It's not like it's not like you have to guess which location you're writing to. You can know that there's always going to be some structure in memory at negative 176 bytes. So you don't have to try to guess something. I'll talk about that a little bit later. So we can write an arbitrary value to, I call it a semi-arbitrary location because you can't really pick any location in memory. We don't know where the stack is because of ASLR, so we can't overwrite the return address. And even if we could overwrite the return address, we wouldn't really know what to pick. And the write is relative to the heap, so ASLR won't impact our ability to overwrite a function pointer on the heap. So what I chose to do was find a function pointer. And there happened to be one that I was able to write to. It's called ptrinfo.lookup. And the cool thing about that is the first argument name also comes from the font file or from the DVI file. So I'm able to call an arbitrary function with an arbitrary first argument, which comes in handy. So what I was able to do is use the width and the height values of this DVI font char structure, which was the array. The array of structures was an array of DVI font char structures, but there's also earlier in memory, or at a lower address in memory, there was a DVI font info structure, which has a function called lookup. So I was able to overwrite the lookup function. So I overwrote ptr input lookup with the address of system.libc. And since name, the first argument was name, is an argument, it's a string representing a font file that it's looking for. So the DVI file specifies that I'm trying to load some certain file, and you give it the name. So what I was able to do is overwrite PTR to put a lookup the system, and the first argument was the location to slash media slash whatever my volume name was slash kill.sh. So the next time that that input lookup call is executed, it calls system on kill.sh, which killed my screensaver. And so the reason I said that this was easier to exploit on a USB device is because I know the exact absolute path name of that kill.sh script, where if I emailed a set of files to someone, I wouldn't really know where they're going to be extracting them when the icons would be generated. So that's why it was much easier to exploit over USB. And I did run into some problems I was very proud of myself for getting around them. The first one was that AppArmor would prevent loading a PK600 file, which is the name of the font file that I was attacking, or the name, the extension for the font type that I was attacking. You can't choose the extension, so the font name is just the name, it doesn't have the extension automatically gets added. So what I did was create a PNG file, and then I made a symlink from the PK600 file to the file name.png. And when AppArmor saw that, it noticed that it was loading a .png file instead of a .pk600 file. I said, okay, I'm going to let this load. Because the AppArmor profile prevented events, or it only allows events to read documents that end in .png, .gif, .pdf, .dvi, etc. So one way to get around that is with the symlinks. And AppArmor won't let me execute the process. So I'm still working on this one, but the idea for getting around that is to use ROP to do a second stage shelf loader. Because AppArmor won't let me map an executable file, like I can't get my own arbitrary executable code in memory. I can create an anonymous write executable mapping, and that is just calling nmap without a file argument. It creates you can create a region of memory that has both writable and executable functions. So if you can create that memory with nmap, call open the file, read that data into the file, then jump there. It should be possible to do that with return-oriented programming and libc, but it takes a lot of effort and a lot of time, and it's really boring, so I haven't spent that much time doing it. So the second stage shell code that gets loaded can do the search for the X11 library and use the X11 APIs to enumerate the root windows and then kill the one labeled screensaver. So the demo that I have for today, it's kind of lame because I ended up disabling ASLR and AppArmor on my virtual machine. It's not really necessary to disable ASLR. I could have had the exploit working with ASLR, but it takes about 5 to 10 minutes to run because it's processing all of these files, like hundreds of files on the USB image. So, So I'm just using a Ubuntu VMware virtual machine. So if I try to log in,